Okay, any questions about anything before we start? Yes, you may ask a question. I forget the details, but I remember it's like you bound from below the probability that something is or less than or equal to something. You know, like it has to do with like the error function and all that stuff. Right. Yeah, I forget the details of that, but it's just a simple inequality, quote unquote, simple inequality. Which one is that? Yeah, Chebyshev inequality on the variance. Yeah. Yeah. Okay. Yeah. Yeah. I don't remember the details. We talked about it when I taught digital communications once. I remember. Yeah. Any other questions? Okay. Regarding the prelim, when I was grading them, it felt like the scores were higher than the first time, but really they were remarkably the same. You know, if you look at everyone's grade, it's almost most people got very close to what they got on the first one, except for a few people. Some people improved a lot, and some people gained a point or two. Some people lost a point or two, but you know, the mean was about the same. It was like 80-ish. The D was about 8.8-ish. So, and those are similar to last year's stats. I don't use those stats in any systematic way. But the moral to me of the story is that it's good to put the old prelims on the website so you can look at them, and it doesn't make any difference, really. I don't know. At least then you know what kind of a test you're going to get. And other than that, also check my addition. Like Alex claims I gave him extra points, so Alex Rucker, so I'll try to take those away after class today if you bring your exam up. And if you have any questions about why one of the ones you got wrong was wrong, let me know. If you've seen it in this first few minutes today already. Question 5 in general. Okay, the key missing word in the problem statement. V is a Hilbert space, and WK is a countable orthonormal subset of V. What's missing? Complete. It's not necessarily a complete orthonormal set. So, certainly item 1 is true because there are 5 mutually orthonormal vectors. They span a 5-dimensional space because they're also linearly independent. And number 4 is true because V is a Hilbert space. It's not just an inner product space. And that's what means Hilbert. Every Cauchy sequence has a limit. But the other 2 are only going to be true when that set script W is a complete orthonormal set. Number 3 is like the definition of being a complete orthonormal set. And number 2 is saying that you can express any V as a limit of that kind. And that only can happen when W is complete. So that's number 5 in general. Any other questions? Yeah.
The very last one, number 9, part 9.
Yes. The sampling. Let me think about that one. That is a good question, actually. That is a good question. Is because a lot of people see what I was thinking for those 2 is the following. 8 and 9 go together. 8 says if the recovered signal is a pure sinusoid, then is the sampled signal necessarily a pure sinusoid? And the answer is no in general, because the sampled signal could have been half of one pure sinusoid plus half of one of its other aliases, added together. The last one says, if the sampled signal is a pure sinusoid, then the recovered signal is a pure sinusoid. That's what I meant to ask. It's true that if you sample a pure sinusoid, if the samples could have come from a sinusoid, then the recovered signal has to be a sinusoid. But you're right that I think, but I have to think about it in detail, that it might be for some omega 1 less than 0. So anyway, probably I processed that possibility out because I was thinking, well, it's a cosine, right? And so greater than 0, less than 0 doesn't matter. So yeah. So anyway, the last one in problem, whatever that is, 9, the sampling problem, that one is on hold. If you got that wrong, you might get it right. The last item in problem 9, the sampling, because of Stephen's question. What? Don't worry, if you got it right, you won't get it wrong. It's only, I give it, I don't take it away on ones where I make a little mistake. Yeah, Denzel.
Explain the third answer for number 6.
The third answer for number 6. Did you try figuring out whether those are orthonormal or orthogonal to each other?
Well, I assume that if it's an orthonormal set, then and because they both include the same methods, then
Did you try to figure out their inner product though? Try it. It comes out to be W1 inner product W1 minus W2 inner product W2 because the cross terms go away. Both of those are normalized, therefore Talmud throws his hands up in despair. Any other questions? That's a good one. Thank you. Okay, so in the remaining time, let's talk some more about SVD. So where were we so far last time? You start with an arbitrary, not necessarily square matrix A with complex entries. You form the Hermitian matrix, A Hermitian A, which is an n by n matrix with complex entries. This thing is going to have non-negative eigenvalues, and there's going to be r positive ones. So those are the only positive eigenvalues of A Hermitian A, and this assumes that the rank of A is equal to R, and the rank of A Hermitian A is the same as the rank of A. Then the singular values of A are the square roots of those things. So sigma j equals square root of lambda j for 1 less than or equal to j less than or equal to R are the singular values of A. And the singular value decomposition of A you get as follows. It's an expansion of A in the following form, the sum from j equals 1 to R of sigma j wj vj Hermitian, where the v's are eigenvectors of A Hermitian A corresponding to eigenvalue lambda j, and that's for 1 less than or equal to j less than or equal to R, and wj is equal to 1 over sigma j avj. That's the singular value decomposition. And I talked a little bit last time about what the terms in this sum look like. They're column vector times a row vector kind of a weird expression. You may not be used to that kind of a thing, but the dimensions come out right. You can think of each term as being an m by n matrix of rank 1. So we're expressing A as the sum of a bunch of rank 1 matrices, R of them. A has rank R. And anyway, so that's, and oh, and by the way, we're assuming that the V's were chosen orthonormal. They, like, from the way I've written it up there, so note that the V1 through VR were chosen as orthonormal. They'll automatically come out to be orthogonal if all the eigenvalues are distinct, but we'd have to normalize them, and if all the eigenvalues are not distinct, they won't necessarily come out to be orthogonal unless we fix them that way. So that makes them orthonormal. And also the WJs are orthonormal because of the way that the V's are, because the V's are orthonormal. Okay, so that's a singular value decomposition. Now, at the very end of class, I kind of dashed off the matrix form of that. Actually, it pays to note that this makes the set W1 up through WR orthonormal as well. Okay, so like I said, at the end of class last time, I kind of dashed off the matrix form of the SVD. What we do is we let capital W be a matrix whose columns are the W's, and how big is this matrix? Reality check here. Alex? N by R? M by R, yes. And V be the matrix that has V's as its columns. And how big is this one?
N by R?
N by R, yeah. And capital sigma be the diagonal matrix whose jth diagonal entry is lambda j, and that's in C to the R by R. In fact, it's in R to the R by R because those sigmas are real. If we let those matrices be defined as that in that fashion, then this is the SVD of A. A equals W sigma V Hermitian. That's the matrix form of the SVD. Okay, so that's where we're at so far. And we haven't told, why do we care about the SVD? Why would anyone ever want to find the SVD of a matrix? All that sort of thing. So that's what I want to get to now. Okay, so the first order of business is, what I want to do is I want to focus on the special case where A is a square matrix, so A is in C to the n by n, and A is invertible. So SVD for a square invertible matrix. First thing to note, in this case, what is the rank of A? If A is an n by n invertible matrix, what is its rank? Victor? N. So in this whole discussion here, R is equal to n. And we have sigma 1, sigma 2, sigma 3, and so on, down to sigma n, and all of them are positive. There's n positive singular values for A. I don't want to say it that way because that implies that's using someone else's definition of singular values as possibly being 0. Okay, so anyway, that's the situation. And all the matrices are square over here. So V, W, and sigma are all square and invertible. So the SVD for A looks like this. The sum form of the SVD is A equals the sum from j equals 1 to n now, because r is equal to n, of sigma j, wj, vj Hermitian. And the vector form, the vector matrix form, is w cap sigma v Hermitian. Because the W and the V are invertible, and because each of them has orthonormal columns, so because the columns of W and V are orthonormal sets, in other words, the columns of W are orthonormal, the columns of V are orthonormal, and there's n of them, we have that W inverse equals W Hermitian, and V inverse equals V Hermitian. So the W and the V are kind of like the capital U we had last time. When we were diagonalizing an arbitrary Hermitian matrix, we had an orthonormal basis of Cn consisting of eigenvectors, and it had that property that W Hermitian and the Hermitian conjugate of it was actually its inverse. Thus, from matrix form of the SVD, A inverse equals, when you take the inverse of the product of a bunch of matrices, you get the product of the inverses in the reverse order. So we get V sigma inverse, which is easy to compute because sigma is a diagonal matrix, times W Hermitian. Right? Because this is V Hermitian inverse is just V, W inverse is W Hermitian, and sigma inverse is that. So note that sigma inverse is 1 over sigma 1, 1 over sigma 2, down to 1 over sigma sub n. Like so. That's easy. And if you expand this out in components, you get this. You get the sum from j equals 1 to r of 1 over sigma j, vj, wj Hermitian. James.
So with that sigma, is it supposed to be the sigma's going down the diagonal with the eigenvalues?
Yeah, it's supposed to be the sigma's going down the diagonal.
Okay.
Yeah, let me fix that. Sorry. Sigma 1, sigma 2, down to sigma sub r. Thank you. That's important, actually. Otherwise, it doesn't come out right. Okay, so now, what do we discover here? We discovered that this thing here is almost the SVD for A inverse. The only thing that's different is that the sigmas, so to speak, which are 1 over sigmas, are ordered in the reverse way. But from this, we can see the following. So this last equation, modulo the ordering of the sigmas, the 1 over sigmas, I'll just call them singular values, is the SVD for A inverse. And in particular, the singular values of A inverse are equal to 1 over the singular values of A. So they're the singular values of A to the minus 1. That's a schematic way of representing this fact. All right, so that's interesting, sort of interesting to note. And I want to note something else, and it's a little more quantitative. So here's a basic fact. In this context, we have the following inequalities. And when I say in this context, I mean in the context where you have A and C to the n by n invertible. That if you take the norm of AV, that's going to be bounded from above by sigma 1 times the norm of V, and bounded from below by sigma n times the norm of V for all V in Cn. And A inverse, and let's use W's here for the A inverse thing, is going to be less than or equal to 1 over sigma n times the norm of W, and bigger than or equal to 1 over sigma 1 times the norm of W for all W in Cn. So what does this tell us? This tells us, in words, sigma 1 is like an upper bound on how much A can expand the Euclidean norm of a vector. So sigma 1 is the quote-unquote biggest expansion factor in terms of Euclidean norms that A can impose on a vector. And sigma n is the quote-unquote smallest compression factor that A can impose on a vector. And the same thing for A inverse. And the only the one for A inverse follows directly from the fact that the singular values of A inverse are 1 over the singular values of A. Now, to see why this is true, it's very easy. You just look at the SVD. So to see why, suppose that V is any old vector, then what is AV? Norm. AV norm is equal to the norm of, let's plug in the SVD. So it's the sum from j equals 1 to n of sigma j, wj, vj Hermitian, all that times v norm. That's by the SVD. Now, this is equal to, if we note that vj Hermitian times v is just, so this is the sum from j equals 1 to n of sigma j. Vj Hermitian times v is just the inner product of v with vj, wj. So far, so good. Since the wj's are orthonormal, this is equal to the square root of the sum from j equals 1 to n of sigma j squared times the magnitude squared of v vj. All that to the 1/2. So that's because the w's are orthonormal. Now, look at that sum. The highest value possible for this sum is going to be, well, maybe I should carry it one step further here. Well, I'm trying to think of it's funny how when I look at the clock and I think I have to fit this in, then I'm trying to think of the shortest cut to the end of the answer, and that's the wrong way to approach these things. Okay, this, first of all, note that the norm of v itself is going to be the sum from j equals 1 to n of magnitude squared of v vj, because v1 up through vn is an ortho basis for Cn. Okay? Therefore, the quantity in here, in this square root sign, if you didn't have the sigma j squared there, you would just have the norm squared of v. But since I have the sigma j squareds there, this whole quantity is less than or equal to what it would be were all the sigma j's equal to sigma 1. So AV is less than or equal to sigma 1 squared times the sum from j equals 1 to n of magnitude squared of v vj to the 1/2, which in turn is equal to sigma 1 times the norm of v. With equality, when v is equal to v1, or v is aligned with v1. Because then the VVJs are going to be 0 for all j bigger than 1, and you would have equality there. Similarly, if you look at the other end of the inequality, don't worry, the proof of this is in the monograph. If you want to read it in a much more orderly way, I think the summary is going to be enough after we're done with this. So I hope. So similarly, the norm of AV is bigger than or equal to what it would be if all the sigmas in there were sigma n's. And if you do that, you get that. And this happens with equality when V is aligned with V sub n. So the conclusion is, the bottom line, we have this. We have AV less than or equal to sigma 1 times the norm of V, bigger than or equal to sigma n times the norm of V. And here we have equality when V is equal to some constant times V1. And the reason it's good to note when you have equality is that you know that the upper bound is actually achieved for some choice of V. And this is equal to equality when V is aligned with Vn. And for the inverse, the result is the same, except the roles of V1 and Vn are reversed. And turned into W's instead. So for A inverse, we have the following. We have that A inverse W is less than or equal to 1 over sigma n times the norm of W, with equality when W is equal to C0 Wn, and bigger than or equal to 1 over sigma 1 times the norm of W. And here you have equality when W is equal to C0 W1. So the W's play the role for the A inverse version of this that the V's play for the A version of this. Okay, so why am I going through this whole thing? Rhetorical question. First, let me give you a piece of sort of like sloppy intuition that's kind of true. What does it mean for A to have a big sigma 1, a big largest singular value? What does it mean for A to have a small sigma n? Remember, they're all positive in this case because A is invertible. So here's a thought that you can keep in the back of your mind. So roughly speaking, sigma 1 large approximately means A has a large entry somewhere. Like it could have, 3, 7, 11, 13, and then somewhere out there, way out in the corner, it could have a 10 to the 59th. And then its largest singular value is going to be on the order of 10 to the 59th, it turns out. Sigma n small roughly means that A has a small entry, not just somewhere, but in a key position, whatever that means. And you could probably guess that the key positions in matrices tend to be sort of close to the diagonal. Okay, now this is really rough. This is really rough, but if someone came up to you in Ho Plaza and said, in a word, in a nutshell, what does it mean to you when I say A has a large singular value? You'd say, oh, well, that means that A has a large entry someplace. What does it mean for A's smallest singular value to be small? Well, that means A has a small entry in a key position. Okay. Sigma 1 is always bigger than or equal to sigma n. And there's this number called, does anyone know what it's called before I tell you what it is? The ratio of sigma 1 to sigma n. It's called Kappa. Does anyone know what the name of it is? Victor? Yeah. The ratio is what's called the condition number of A. Note that kappa is at least 1, but it can be arbitrarily large. Like if A has a 10 to the 59th someplace and the 10 to the minus 59th in a key place, then what's going to happen is K is going to be on the order of 10 to the 108th, turns out. We say a matrix A is well conditioned, whatever that means, when kappa is close to 1, and ill conditioned when kappa is much bigger than 1. So when kappa is not too much larger than 1 and A is ill-conditioned, I always thought that was kind of a funny term, when kappa is much bigger than 1. What does well-conditioned mean? What does ill-conditioned mean? It means that A is suitable for numerical computations when it's well-conditioned and unsuitable for numerical computations, roughly speaking, when it's ill-conditioned. So let's get quantitative about that. So roughly speaking, again, well-conditioned roughly means that A is quote-unquote suitable for numerical computations. In other words, what does that mean? That is to say, I ran into a bad piece of chalk at a key time. That is to say that the inevitable things like round-off errors, finite precision effects, and all that kind of thing, so round-off errors, etc., don't result in huge errors in numerical computations involving A. So don't give rise to huge effects. When doing computations involving A. Okay, so what do we mean by don't give rise to huge effects? It's pretty rough to just say that without putting any kind of quantitative meat on it. So let's get a little more specific. So let's consider a specific problem. Say you're given V in Rn, or Cn, you want to compute W equals AV. That's a very typical kind of problem you might want to do numerically on a computer. You take a vector, you multiply it by a matrix, you get another vector. Okay, so what's going to happen here? You think of V as the data. So V is quote-unquote the data. And W is quote-unquote the answer. What we want to do is we want to get a grip on how much an error in specifying the data affects the answer. So here's a question. How sensitive, whatever that's going to mean, is the answer to an error in specifying the data? And the way people approach that is as follows. They say, okay, well, the data are, or is, however you want to think of data. When I was a kid, data was definitely a plural, but nowadays it's becoming acceptable to use it either way, depending on the context. So think of V hat as some nominal data, and V tilde as an error in specifying v hat. Then w hat, which is going to be a v hat, is going to be the nominal answer. And w tilde, which is a v tilde, is the error that arises due to the error in specifying the data. So I'll just say the error that arises because of v tilde. And the sensitivity measure that people consider, and I've thought about giving this a name, but I'm not going to do it in class at least. The sensitivity measure is the percent change in the answer divided by the percent change in the data. That's a reasonable measure of computational sensitivity that gets rid of things like units and sizes and all that by looking at percent changes. And how do you model the percent change in the answer divided by the percent change in the data? The percent change in the answer is going to be the norm of a, or the norm of w tilde divided by the norm of w hat. And the percent change in the data is going to be the norm of v tilde divided by the norm of v hat. That's the way people model it. Okay? Now the percent change w tilde is going to be a v tilde norm. W hat is going to be a v hat norm. And that's going to be divided by v tilde over v hat norms. And now in come our singular values to the rescue. What do we know? We know from the SVD and actually I'm going to leave this up temporarily so we can look at it. So from the SVD, we have that the norm of a v tilde, the biggest that can possibly be is sigma 1 norm of v tilde with equality when v tilde equals vn, or is aligned with vn, or v1, I mean. And AV hat is at least equal to sigma n times v hat, with equality when v hat is aligned with vn. And if you plug in those inequalities to the sensitivity measure up there, you get this. Sensitivity is bounded from above by sigma 1 v tilde norm divided by sigma n v hat norm divided by v tilde norm over v hat norm. And that's equal to sigma 1 over sigma n equals kappa. With equality, the worst case when the data are lined up with, or is lined up with, the smallest singular value vn, v thing, which is vn, and the mistake, the error, is aligned with the largest. Now this makes sense because why? Because when A operates on a vector, the direction of the largest singular value, namely v1, is going to be the direction it amplifies the most. So if you have the error in that direction, then the error is going to get amplified the most. If the data is in the direction that it amplifies the least, then the error is going to get amplified over the data. Okay? So the bottom line is the condition number measures in this quantitative fashion how sensitive numerical computation, that particular numerical computation involving A, is to errors in the data using the sensitivity measure we have up there. Now, it turns out that the same exact thing holds for computing V given W in the equation W equals AV. We'll do that next time real quick. And then triage things to figure out what to talk about on the last day. Okay, anybody come late and want to get his or her test back?